Hi, I'm Brock Archer.
And I'm Ron Moore.
Electric vehicles are growing rapidly in popularity, and rescuers need to be ready for anything that they might encounter at roadway incidents. One electric vehicle manufacturer that's really leading the way is Tesla Motors, with the release of their new Model S. It's a fully electric sedan that in many ways has redefined the possibilities of electrically powered transportation. In this video, while using the Model S and the Tesla Roadster as examples, Ron and I will walk you through the various components that electric vehicles possess. We'll cover the hazards that they present to rescuers and provide the simple procedures that'll help you safely operate at incidents involving EVs.
As responders, increasingly we have the probability of arriving at a vehicle-related incident that is in fact an electric plug-in vehicle. Since the late 2000s, we might have had 100 or so electric vehicles on the road. And now the number is thousands, and it's growing. So as our prevalence to arrive at a scene and find an electric vehicle increases, so do the myths and the realities, the urban legends and the truths. So another thing we'll do in this program is address some of the misinformation about electric vehicles. There are risks, there are hazards, and all that needs to be managed. So no, you won't be electrocuted when you step into the water to work at an incident involving an electric vehicle. And no, you won't be electrocuted when you take your power rescue tool and try to pry a door open. We'll take care of those urban legends right off the bat. But we'll show you in more detail what the reality is about how to safely, effectively, and efficiently manage an electric vehicle incident.
Let's take a couple of seconds and look at the basic electrical concepts that we need to understand before we operate at an incident involving a high voltage vehicle.
In order to better gauge the potential dangers of high voltage electricity found in electric vehicles, it's important to understand the concept of an electrical circuit or path that electrical current will follow. Whether we're discussing direct current or alternating current, they both share a common element. For the current to flow, there must be a completed path for the electrons to move along. Let's use a hose line as an analogy. If the bail of the nozzle is closed, now current is not flowing, but once it's open, the current flows. Similarly, your wall outlet has 120 volts available, but no amps are flowing until you plug an appliance into it and turn it on. Injury from electricity occurs when we place our body in the path or become a conductor for the current to complete a circuit. DC currents are usually found in devices that are powered by batteries. In order for power to flow, there must be a continuous connection or circuit from the negative to the positive side. In this example, the electric circuit conducts current from the battery to a motor and powers the motor, then flows back to the battery. If that circuit is broken, for instance, by a switch in the path, the current will no longer flow. Therefore, touching one side of the circuit will not result in an electric shock, because there would be no completed path for the flow of current through your body. If you touch both sides, completing the circuit, however, you could be in for a shock. To receive a shock, you must make contact with both the hot and negative sides of the circuit. Lack of an earth or chassis ground connection means that simply touching one side of the circuit, you will not receive a shock.
Now that we've looked at the basic electrical concepts involved in an EV, let's take a look at the different components that they possess and how they'll affect our operations at an emergency incident. Let's take a minute and look at the AC motor that powers the drivetrain and the inverter converter unit. Most production electric vehicles utilize an AC motor to power the drivetrain. But because the battery produces DC current, this power must be converted from DC to AC before it can be used by the motor. In addition, many EVs are equipped with regenerative braking. This means that when the motor that normally powers the vehicle is still spinning but not being used to power the vehicle, like in the case of regenerative braking or coasting, The motor's spin actually produces AC electricity and recharges the high voltage battery. But because the battery is a DC battery, this energy from the AC motor must be converted to DC before it can be sent back to the battery. It's a little tricky, but this conversion-inversion of AC to DC and DC to AC, it all takes place in the vehicle's inverter-converter unit. The important thing for rescuers to understand is that high voltage power is present in the inverter-converter unit, and this unit should never be cut or crushed. Now let's take things a bit further. Inside the inverter-converter unit, we'll also find high voltage capacitors. Capacitors store and release energy, and in electric vehicles, they're used for smoothing out the power traveling from the motor. But for rescuers, capacitors could present a serious hazard of shock because they can release up to 400 volts in just an instant. Another reason why we never want to cut into the inverter-converter unit. In the Tesla Model S, the inverter-converter unit is actually located in the motor housing between the rear wheels of the vehicle. The likelihood of rescuers interacting with this unit is unlikely because of its location. But in many EVs, the inverter-converter unit is located under the hood. Because of this, blindly forcing any conductive tools under the hood should be avoided.
The flow of electricity from the high voltage battery is controlled by relays or contacts inside the battery. When the 12 volts direct current is applied to the relays, they close, and the high voltage circuit is complete, allowing current to flow. When the 12 volt current is removed, the relays open, shutting down the high voltage outside the battery. We'll show you the actual procedure in a bit, but keep this in mind because it's an important concept for disabling an electric vehicle.
When talking about electrical systems on electric plug-in vehicles, we're actually discussing two separate systems. All electric plug-ins have a low voltage system. That would be the 12 volt. The 12 volt that's grounded to the vehicle, to the structure of the vehicle. And that's what we're used to. That's what we run up against with internal combustion vehicles as well. In addition to the 12 volt low voltage system, the electric plug-ins will have the high voltage. Because they've got two electrical systems, they also have to have at least two batteries. One would be the 12 volt battery, and one or multiple batteries would be the high voltage. Now, when you look at an electric vehicle overall and you're trying to locate those batteries, one place to start for the 12 volt would be up front, typically raising the hood. That would be the most likely location for the 12 volt. The other location would be towards the rear of the vehicle in the trunk or liftgate storage area. Now, the high voltage battery, or batteries, there can be multiple ones, can be in a couple different locations. Everything from the front end. We may find the high voltage battery physically inside the car, running between the seats or literally beneath the second row seat cushions. We may find the most likely location, the trunk, again, liftgate, rear area of the electric vehicle. Now, on this particular Tesla Model S, it's one of the electric cars that has a high voltage battery located in the floor pan area beneath the metal bottom tray of the car. That's really interesting, and I want to show you that. I have a vehicle that they have lowered the high voltage battery, separated it from the car, and we're going to go over and take a look so you'll see how the floor pan high voltage battery is designed and how it's mounted into the electric plug-in vehicle. Let's go take a look. We're underneath a Tesla Model S, and they've lowered the high voltage battery for us. This is a 1,000 pound, 400 volt high voltage battery that is mounted beneath the floor pan. You can see the floor pan up here. This battery will be secured beneath that. Rockers on both sides. It'll run from the rear axle to the front axle. Directly above me is the electric motor. This is a rear wheel drive electric plug-in automobile. Now, the high voltage battery, in this particular case, it's a 400 volt, as I mentioned. It's lithium ion chemistry. As a responder, the way these batteries are made, for us to understand, it's like slices of bread that make up a loaf of bread. Cells in a high voltage battery are connected together. Cells make up modules or bricks or sections that make up the whole battery. So you have individual DC cells that are combined and connected together to form a battery that you see here. Now, for a firefighter, for a first responder to a vehicle incident, the high voltage battery does present a degree of risk, and it's something that we need to manage. If the NHTSA, National Highway Traffic Safety Administration, has introduced guidelines that tell us things to look for when we're trying to make an assessment to see if the battery itself might be damaged. If it is, there's a whole different protocol for us to follow.
Let's take a look at the DC to DC converter. This is the alternator for electric vehicles. EVs don't have a motor that can turn an alternator and recharge the 12-volt battery, so they use the DC to DC converter. It's pretty simple. Here's how it works. High voltage current travels from the battery into the DC to DC converter. There, it's converted into 12-volt electricity, which then travels to the typical 12-volt battery, like we find in most vehicles. It recharges that battery and acts as a second 12-volt system for the vehicle. The location of the DC to DC converter in an electric vehicle varies, but on the Model S, it's located in the wheel well on the passenger side of the vehicle, just inside here. Because of this unique location, it makes dash displacement evolutions a little challenging for rescuers. Later, we'll show you how to work around the DC to DC converter when it's in the wheel well location when we get into showing you the different evolutions.
So what about cabling that responders might find when you arrive at an incident involving an electric plug-in vehicle? I have here some bright orange, traffic cone orange color sheathing that goes over cabling. If you arrive at an incident and find cabling, sheathing, or connectors of this color, it meets the SAE standard that describes more than 60 volts DC or more than 30 volts AC is in fact flowing or potentially could be flowing through that cabling. Now, there's a teaching point about this that I want to make sure you're aware of, related to electrics and related to hybrid vehicles as well. All orange cabling that you find on an electric and all orange cabling you find on a hybrid vehicle are in fact high voltage, more than 60 DC, more than 30 AC. However, it's not all high voltage cables are orange. So, how do you get around that? Here's how I teach. If you're at an incident and you find a colored cable, and I'm not talking a piece of speaker wire, I'm talking jumper cables. If you find something large and it is of a color, whether it's orange or blue or yellow, let your officer know, get together on it and decide. It may in fact be your first indication that you're dealing with an electric vehicle. Be on the lookout for colored cables. They're trying to tell you something. So how does a first responder identify that the vehicle involved in the incident they've responded to is in fact an electric plug-in vehicle? There's formal and informal means. I want to talk about that and show you what that means to us as a first responder. Formally, the automakers will identify around the exterior of their vehicle with what's called badging. On this Tesla Model S that we have here, we have the Model S logo or exterior badging at the rear. The most common location for exterior badging on electric vehicles is one side or the other at the rear. In this case, it's actually on the lift gate. It could be on the trunk or on the back of a sedan type vehicle. Now, in addition to a single point badging that you see here, automakers can do a 3-point badging system. With that situation taken into consideration, I may find somewhere on the driver's side of the vehicle as well as somewhere on the passenger side, maybe on the door panel, maybe up on the trim of the B-pillar, and in this particular case on this Tesla, all the way up here on the front quarter panel, front fender, we see badging here and badging on the other side. So this automaker uses a 3-sided option for exterior badging. Now, it does not say electric, it does not say EV. what it says is it uses, the one measure is a unique name, Tesla Model S. The only Model S vehicles produced are all-electric plug-ins. So automakers can use EV or the word electric, for example, in the badging, or this option, unique names. So those are formal. As you approach a vehicle from a distance, you may see this exterior badging. On other electric vehicles, it may not be until you, in fact, raise the hood. And when you raise the hood, you might see words inside or emblems inside. You may find orange cabling, meaning the high voltage cabling is there as well. It may be that when you get inside the vehicle, you see what's called an interior marker. If they only do a single-sided, which would be the rear, single-sided exterior badging, then the recommendation is to have at least one interior marker. That would be an emblem or an icon or a name or the word electric or the word EV within the proximity of where I would be starting or powering down the vehicle, and that would be, again, an informal means of identification. In addition, if my vehicle owner is conscious and alert, they may be able to tell you, in fact, this is an electric plug-in vehicle that they are involved in or that you, as a responder, are working with. So responders can pick up exterior formal and interior informal, maybe under the hood informal means, only if you're alert to the fact, and if you're thinking about what type of vehicle is this, I need to identify what I'm dealing with. The secret of knowing you're dealing with an electric is identification. It all starts from there. So identification, be heads up when you arrive on the scene. Anticipate that every vehicle you respond to could in fact be an electric plug-in vehicle, and let that set the stage for how you operate when you're first due at an electric vehicle incident. So charging an electric vehicle, what do first responders need to know? There's a couple of important points. Let me start by explaining the charging process. On this Tesla Model S, I have a charging port built in this driver's side rear area. Simulating that I'm in a garage at my home and the vehicle needs recharge, I simply would take the charging cable and power it off the house electricity. I would plug it into the charging port. On this particular model, the way it's designed, blue means I'm secure and the green actually means that I'm charging. Now, the charging port only accepts electricity flowing into the vehicle. Of concern to first responders, if the power were shut down in the neighborhood or the power were shut down at this house, no, the power in the battery will not flow out and will not energize circuits in the building or in the structure. In addition to recharging by plug-in, electric vehicles also can recharge their high-voltage battery in a process called regenerative braking. As I'm driving the vehicle and as I either coast or use the brakes, the AC motors up front that are working to drive the unit actually turn into generators of such and send electricity back to recharge the battery. So there's a couple of different ways to be recharging of an electric plug-in vehicle.
Shutting down the high voltage and isolating it to the battery pack is absolutely critical if we're going to be doing any cutting or crushing on the vehicle. Of course, we can never shut down the high voltage to the battery itself, but we can isolate the high voltage to the battery by opening up the contacts. There's a few ways we can do it. Most vehicles are equipped with two different types of disconnects: safety disconnects and service disconnects. As rescuers, we want to use the safety disconnect and try to avoid using the service disconnect. A little more on service disconnects in a second. Safety disconnects are built into EVs for first responders. They can often be found under the hood of the vehicle, and occasionally we'll find them in the trunk or luggage compartment of a vehicle. They're generally marked very well for rescuers to find. Here we have a safety disconnect marking on the Tesla Model S under the front, which would be the hood, but they call the frunk area of the vehicle. and it's marked here for rescuers. You can see the firefighter helmet and the cutters showing us that there's an operation that they want us to do under the hood. With the panel removed, we can take a look at what they'd like us to do. Here we have the label wrapped around the wires that we need to cut. It's two little tiny wires, they're 12-volt wires, and by just simply cutting these wires, we can shut down the high voltage. What it does is it takes the 12-volt power that was being sent to the contacts in the high voltage battery, and it takes that power away, thus opening the contacts and isolating the high voltage to the battery. If we're unable to access the cut loop or the safety disconnect, we can actually cut the 12-volt battery. We're going to want to cut the 12-volt battery anyway to shut down the SRS system and to just immobilize the ignition of the vehicle. Battery locations vary. We'll find them under the hood. We find them under the seats of vehicles. We find them in the luggage compartments. After we locate the battery, we always want to cut the negative terminal first and then the positive terminal. We also want to remember to double cut both of our terminals because the memory in the cabling can bring them back together after we've cut them. Many electric vehicles have not only a safety disconnect, but they also have what we call a service disconnect. Generally, service disconnects are actually located on the battery itself. And this is a high voltage connection. So when we pull a service disconnect, we're actually opening the contacts in the relay. Generally, manufacturers recommend that only service personnel use the service disconnect. Now, some manufacturers recommend that rescuers use them. Most late model vehicles use a proximity key of some type that, as you approach the vehicle, unlocks the doors and allows you to gain access to the vehicle. The Model S is no exception. Here I have the proximity key for the Model S in my hand. This key, when I approach the vehicle, unlocks the vehicle and allows me to make access. For rescuers, proximity keys shouldn't be a huge concern. We don't want to spend a lot of time looking for the proximity key. If one's found, we take it 16 to 18 feet away from the vehicle, but again, don't spend a lot of time hunting for it. One thing that makes the Model S different than any other vehicle is that it doesn't have an on-off switch, and there's no key to turn to put it in a ready-to-drive position. We simply sit down on the driver's seat, and the seat switch makes the vehicle ready to drive. We'll show you how it looks. As you can see, when we sat down on the vehicle, the screen actually changed modes, and now we're into the driving mode of the vehicle. From here, we can put the vehicle into gear and drive it like a normal electric vehicle. With the Model S, it's even more important that we utilize the 12-volt battery, we double cut the terminals, and we use the safety disconnect loop and cut that to make the vehicle safe for our operations.
Attention. Looks good.
All right, good job, guys. So stabilization of an electric plug-in vehicle, side resting as we have here, what's different? A couple of things. This is a Tesla Model S, and the battery, the high voltage battery, is a floor pan mounted unit. What you're looking at here in the shiny black is the underside of that battery casing. It occupies an area that we typically use for stabilization of other vehicles that we're used to. Not so when we have an electric vehicle with a floor pan battery location. We're going to have to find alternate stabilization points. We have a 3-strut stabilization here, and 1 strut we use this rocker area across the top. So all of that would be in play. We might find something strong at the back of the vehicle or something strong at the front of the vehicle, but we can't use any bracing or any strut type equipment up against this floor pan. The second difference that you'll find with electric plug-in cars, if it is a battery that's mounted in the floor pan especially, the center of gravity can be off. They might not be engine heavy like we're used to. So the center of gravity on this particular car is relatively low because the weight is the battery. It has a tendency to be heavier to one side or the other, something that we're not normally used to. Other than that, cribbing, step chocks, any other devices or systems that we have are in play as far as stabilizing it. Avoid the floor pan area, meaning the battery area, and be alert to the shifting of the vehicle due to its center of gravity being slightly different. If you can keep those 2 concepts in mind, you'll be able to safely and effectively stabilize an electric vehicle side resting.
When we receive an extrication assignment, we need to get into the mindset that anywhere we're going to cut or crush, we need to expose that area of the vehicle and look for hazards. We need to be looking for airbag inflation cylinders, seatbelt pretensioners, SRS control units, and high voltage components. We also need to, when we respond to a traffic incident and we've discovered that we're dealing with an electric or hybrid vehicle, one of our first operations needs to be immobilization. Because the vehicle moves silently, it's important to chock the wheels, all 4 wheels, right away before we start any evolution on the vehicle. Earlier we looked at the different locations where we find the different components in the Model S. And the DC to DC converter was in an area that could challenge rescuers when dash displacement was required. We're going to now look at some workaround techniques for effective dash displacement when we have high voltage components in that location. When we have a dash lift or jacking the dash assignment on a late model vehicle, it's more important now than ever to remove the quarter panel and the hood to gain access to the body structure of the vehicle so that we can make good complete relief cuts before we go to lift or roll the dash. We'll have the guys come in and remove these body components, and then we'll get into making our relief cuts for our dash roll evolution. Now with the quarter panel removed, the hood removed, and the door off the vehicle, we can take a good look at what we're dealing with. We see the location of the DC to DC converter there on the wheel well. Now typically with a dash displacement evolution with a late model vehicle, due to the body structure strength, we would need to cut completely through the A-pillar in order to move the dash. Instead, what we're going to do is we're going to cut as far through the pillar as we can without getting into the DC to DC converter. Keep in mind, in the Model S and in many electric vehicles, the high voltage cabling actually runs through the rocker of the vehicle. So if we choose to push off the rocker for our dash displacement, we want to monitor that rocker to make sure that it does not crush down onto the high voltage cabling. So we're going to have the guys come in and make some cuts in the A-pillar. They're going to get as far through the pillar as they can, and then we'll have them go up and make their relief cuts in the upper rail and the body structure in the front end. let's take a look at the body structure in the front of the vehicle. It's a little different than what we're used to, so we've got to make some different cuts. If you look at the upper rail in the Model S, it has a cutout area here where we're going to need to separate it from the strut tower. So we're going to have the guys make a relief cut here in the upper rail, but that's not going to be enough in the Model S. Typically, that would be sufficient, but we've also got a connection from the upper rail to the strut tower here that we're going to need to cut. So we're going to have them cut here, and then we're going to have them create the separation here as well. We've also got some reinforcements coming off the dash bar that go out to the strut tower. These will also have to be cut in order to get good movement in the dash. Okay. Now with the relief cuts all in place and our cut as complete as we can make in the base of the A-pillar, we just need to make one more relief cut before we go ahead and roll the dash. That's going to be the dash tie downs. With this newer, stronger vehicle construction, dash tie downs could be the difference between getting the dash all the way off the occupant or not enough. So we can expose that center console area, we can look for those dash tie downs and make sure that we cut them. If we don't have a passenger in the vehicle, they're fairly easy to access. If we have two occupants, the rescuer needs to get between the driver and passenger seat and access that area. Now with the dash tie downs cut, we can take a look at ramming the dash forward. Again, because of the body structure and the strength of the body structure on late model vehicles, we want to get a good point to push on the A-pillar. When we push up high on the pillar, we run the risk of the pillar actually ripping and the dash not moving forward. So what we're looking for is some good reinforced area to push on. In this case, behind the hinge backing is a good place to push. So a good option for us is to put the ram head here and push in this area. We'll let the guys show you what it looks like. Now with our dash displacement complete, you saw we started with a dash roll evolution, and then we were able to bring the spreaders in and turn it into a dash lift evolution, or jacking the dash evolution. You can see that our DC to DC converter was untouched. We kept it complete and avoided the hazard. In this video, we presented some ideas and concepts that we hope will help keep you safe at incidents involving electric vehicles. The intention of this program is not to be a standalone presentation or training for EV response, but to accompany training that you receive from a qualified EV instructor. Please take a look at the Tesla Motors EV Response PowerPoint presentation, the Emergency Response Guide, and the quick reference card for the Model S. Thanks again to Tesla Motors for providing this valuable training. I'm Brock Archer. Thanks for watching.